All right, so I already started filling out some of this just to save time because it takes me forever to write on this mouse. All right, so as we're, just to review kind of what we did yesterday, everything, I like the way the problem was set up better on the other one where everything was kind of organized a little bit better in the information, and that's the way it normally is. But you have all your 6 things here on the left, your X and Y intercepts, whether it's even or odd, and then your 3 asymptotes. Now remember, since this is a polynomial, there are no asymptotes. So that's why I have a little slash here with the vertical asymptote, horizontal asymptote, and the slant asymptote. Okay, so for the x-intercept, I got 0, 0, and 5, 0. The way I got that is I set the original equal to 0. Nothing to do with the derivative when you do these first 6 things. All right, it's the original. So I set the original equal to 0. You see that right here. I took out an x to the 4th, which left me with x minus 5. So I set each of those equal to 0. The x to the 4th gives me 0. X minus 5 gives me 5. So that's why I have 0, 0, and 5, 0 as my 2 x-intercepts. To get a y-intercept, you substitute 0 in for x. So we get 0 to the 5th minus 5 times 0 to the 4th. That's just 0 minus 0, which is 0. All right. If the x-intercept is 0, 0, the y-intercept will be 0, 0. All right. So that's the x and y-intercept. To get even or odd, all right. Remember, even to figure out even or odd algebraically, you plug in negative x in for x. If you get the original, that's even. If you get negative f of x, that's odd. So when I plugged in negative x, I get this, negative x to the 5th minus 5x to the 4th. Well, that's not the original, x to the 5th minus 5x to the 4th. In order for it to be the opposite, it would have been negative x to the 5th plus 5x to the 4th. That's what it would need to be if it was odd. Well, this is not, all right? It's negative, negative, that's plus, that's a minus. So that's why I got neither. All right, so all 6 of these things here have to do with the original function. All right, all 6 have to do with the original function. All right, any questions on those first 6 things? All right, now this next set has to do with the first derivative, which I boxed here in the pinkish reddish color, 5x to the 4th minus 20x cubed. All right, so that's my first derivative. So to find the critical values that go on the number line, I set that equal to 0. And I take out a 5x cubed, which left me with x minus 4. So that gives me a 0, that gives me a 4. And that's why I have 0 and 4 on my number line. And then substitute in values, and it happens to be positive, negative, positive, all right, which leaves me with increasing from negative infinity to 0, union 4 to infinity, decreasing from 0 to 4. At 0, I have a relative max, and at 4, I have a relative min. Now, to get those y values, how I got negative 256, I took 4 and substituted it in for x into the original. All right, this is to the original. So anytime you plug in the original, once you get this increasing, decreasing stuff is when you're finding y. Now, it happened to be a really big number, right? I used a calculator. It was like 1024 minus 1280 or something like that. So trust me, it's negative 256. Hopefully you guys got that. All right, so then we got 0, 0. So we have all of that stuff. So hopefully by now, the increasing, decreasing, and the concavity part is becoming pretty straightforward. All right, so then move to the next, and we have the second derivative stuff. So the first derivative was 5x to the 4th minus 20x cubed, which means the second derivative was right here, 20x cubed minus 60x squared. So to find those critical values, I set those equal to 0. I take out 20x squared, leave me with x minus 3. And when I substitute values in, anything less than 0 give me a negative. Between 0 and 3 also gave me a negative. And anything greater than 3 was a positive. So that means it was concave up from 3 to infinity and concave down from negative infinity to 3. All right. So then any points of inflection are where it changes. It doesn't change at 0. It's negative and negative. It's then bigger than 3 it's greater, concave up bigger than 3. All right. Then it changes from negative to positive. So that's why we have our point of inflection at 3. And when I plugged in 3, I got negative 162. Sorry, close the door there, a little noisy. All right. So any questions on the second derivative? All right, so that stuff is kind of like all like older. We've done it. All right, so now I haven't done this yet, is the steps how you would do the big number line. Remember, the big number line we do based off any critical values that I had on either the first derivative or the second derivative number lines. So on the first derivative, it was 0 and 4. On the second derivative, it was 0 and 3. So it means I got to put a 0, I got to put a 3, and I got to put a 4. Okay. Then on the top, I look at the increasing one, and it tells me increasing, decreasing, the first derivative, where it's increasing and decreasing. So up above, it said that it was increasing less than 0 and greater than 4. And then between 0 and 4, it was decreasing. Now I have this other 3 in here, but that's okay because I need that interval. All right. You need to have all these different intervals. Then on the bottom, I put the concavity. Well, the concavity is right here for me. Concave up 3 to infinity. So from here up, that means this is up, and everything less than that is down. So that's down, that's down. And what this is telling us is what the curves are looking like at, in these intervals. So, and it's good to start with these examples because this one has, these first couple examples have every curve that there possibly is. That doesn't always happen. All right. So increasing and down is that, decreasing and down is this, decreasing and up looks like this, increasing and up looks like that. Right. And like I said, eventually you don't have to draw those there. I'm just doing that so we can review what they look like. You could just do them as once you plot all your points. All right. So then the last step is to go through and plot our points. And first off, if there's any asymptotes, we don't have any asymptotes, so we don't have to worry about that. So our x-intercepts were 0, 0, and 5, 0. We then had our y-intercept was 0, 0. We had a, what was it? Let's see. And our point of x was 3, negative 162. 4, negative 256 was a relative min. Okay, so it's like, well, how do I put that on there? Well, put a spot here for 4, and then just put it down here, negative 256. That's all you have to do. And there you go. 4, negative 256 is right there. Then we had 3, negative 162. All right, well, that's bigger than 256, so it goes up higher. And I label that 3. And there we go. All right, so there are points. I don't think that was a point of inflection. That was a relative min. This 0, 0 is also relative max, which we already have. So those are our points. Then we just play dot to dot. All right, we just connect it. And we make sure that, so anything less than 0 has to be increasing and down. So increasing and down looks like this, right? That's increasing and down. Then we went decreasing and down. Then we changed to decreasing and up. And then this goes to increasing and up. And this will make sure that's concave up. All right, it goes through like that. Should be a little bit more spread out there at the end, but you guys get the idea. All right, any questions on any part of this, especially the big number line and how we graph that? Okay. All right, so that's a polynomial. All right, most polynomials, obviously, if it's negative out front, it's going to change things, but it's going to have the same basic kind of flow to it. They're going to be pretty, obviously each graph will look a little different, but the same sort of setup. All right, so what I would like to do now is, where is it? I just had it up. Oh, there it is. Nope. All right, so this is from our other page we were working on before. And we're going to work on this example right here, which is a fraction. And what happens when we have a fraction? And if you notice, we have all the same information we're asking for, all right? We're starting out with the same 6 things, all right? And that's the way when we do these problems, what's going to happen? vertical, horizontal, or slant asymptotes, x-intercept, y-intercept, and symmetry. Okay, so this all has to do with the original. All right, so let's start with the asymptotes. The key is just knowing how to do each one. And then it's all a bunch of different little things. The actual math involved is not that difficult. It's just knowing what you're supposed to do for each one. So with a vertical asymptote, I set this equal to 0. All right, I set that equal to 0, and that gives me x equals 2. There's my vertical asymptote. My horizontal asymptote is determined, or slant, by looking at the degree. The degree is 2 on the top, 1 on the bottom. Larger on top means there is no horizontal, it is a slant, which means we need to do synthetic division. All right, meaning I'm going to put a 2 in the box. Why do I put a 2 in the box? So that makes that equal to 0. I put a 1, a -2, and a 4. That happens because 1 comes from the coefficient of x squared, -2 from the coefficient of x, 4 from the constant. Do synthetic. I bring down the 1. Whenever there's a number down here, I multiply by the box, and I put it here. I add these numbers. I get 0. You don't need to go any further, but I will, because this remainder means nothing. I don't care about that. So the remainder means nothing. The number to the left of the remainder is your constant. Well, it's 0, so I don't know that. This is your coefficient of x. So my slant asymptote is y equals, and then I have 1x, which is just x. So that's going to be the equation of our slant asymptote, which we're going to have to graph. So now we have asymptotes involved. So it's a little different from the polynomials. Questions on how I got those asymptotes? Okay. X-intercept. All right, now remember, for x-intercepts, I said set the top equal to 0. Even if it was a polynomial, it doesn't matter to set equal to 0. Well, here it really makes a difference because there is a top and a bottom. So I want to set this equal to 0. Well, I can't factor that. X squared minus 2x plus 4. So I would have to do potentially some completing the square or a quadratic formula. If you can't factor, here's a little advice for you. If you can't factor it, that means it's imaginary zeros. I'm not going to give you one that is going to have x-intercepts that are like 3 plus or minus root 5. It's not going to happen. So if you can't factor it for right now, guess what? It's imaginaries, which means there are no x-intercepts. There's nothing that makes the top equal to 0 here. No real numbers, so it's imaginary zeros. And it is possible not to have an x-intercept. To get a y-intercept, I plug in 0 for x. So that's 0 minus 0 plus 4 over -2, which means 4 over -2 is -2. So my y-intercept is 0, comma, -2. All right, 0, comma, -2. Symmetry, I plug in -x. So I get -x squared minus 2 times -x plus 4 over -x minus 2. All right, so that's positive x squared minus 2x plus 4. You can tell right away this is not going to be either, because when one thing on the bottom changes but not the other, it's not a good sign that you're going to have, it can't happen. It can't be the same and it can't be the opposite. Here, same thing. You have one thing change it. You have one thing stay the same, one thing change, another thing stay the same. All right. It's neither. All right. It's not saying the same. It's not the opposite. All right. Like I said, when in doubt, say neither. And if you think about it, the last graph we just did, the polynomial, that had no sort of symmetry to it. Right? And you can tell after you graph, like, oh, wow, that looks symmetric. We should probably have some sort of symmetry. Let me go back and check. And in this case, this one does not. All right, so now we're all done the top stuff. All right, so why don't you take a couple minutes here and see if you guys can get critical values for the first derivative and the second derivative, and then find where it is increasing, decreasing, and all the concavity. Remember, all right, set it where it's equal to 0. Actually, let me get you started here for a second, because I just want to review this real quick. So when I do this, and I set the top equal to 0, I take out an x, and I get x minus 4. All right, so it means 0, and 4 are critical values. All right, easy enough. Set the bottom equals 0, I get 2. So when you do this, I get 0, 2, and 4. You have to remember what is happening at 2. And we wrote it down, right? It's a vertical asymptote is happening at x equals 2. So remember with these problems with the fractions, you have to be aware that potentially you have to split up the intervals of increasing and decreasing, or you can't have points on that. All right, go ahead and see if you can get the rest of this section before we actually finish graphing it.
Mr. Dillon.
Yep. Yeah, go ahead, Caitlin.
What you used the synthetic division for? Like, was that for the slant asymptote?
Yeah, so whenever we knew there was a slant because the degree was larger on the top than it is on the bottom, okay? So that tells us right there that there is no horizontal, it has to be a slant. So we have to divide in order to find it. So I mean, you could do long division. I just think it's easier to do synthetic. And I would only give you ones that were like this, where it's not going to be like an x squared at the bottom, so you could use synthetic. And our slants that we have to graph would always be like y equals x, or y equals x plus 2, or y equals x plus 3. Nothing too crazy.
Why did it wind up being y equals x then?
Okay, so do you understand how I got like these numbers on the bottom? Like the 1, the 0.
Like the last part, like how can you just do like 4 at the end? Like why did you do x?
Okay, because so that 4, we don't use the remainder when we're doing the slant asymptote. The remainder has nothing to do with it. So what this really means is like if you were to divide this, it means it's x plus and then 4 over x minus 2. That's the remainder. We don't worry about the remainder. The number to the left here, say that was a 2. Then that 2 is our constant. The next number is our coefficient of x. So it's y equals this thing, which is x, plus 0, but we don't really ever write plus 0. So if that was a 2, then we would write a 2 there. If this first thing was a 2, I would have wrote 2x instead.
Okay.
Okay. Let me see what he doing. Lucy. Sorry, my dog just took my shoe. Lucy. All right, so when we are plugging in, all right, now we're plugging into the derivative. The bottom, and this is always things that you want to do to like make sure that you are saving time, like not wasting time. Like don't plug into the bottom because you know the bottom, anything squared is always going to be positive. So only need to worry about the top, like the x times x minus 4 part. So when I plug in a negative number, -1, that's a negative on the outside, negative minus 4 would still be a negative, and negative times a negative is a positive. If I plugged in -1, that would be, positive 1. It's a 1 between 0 and 2. that would be a positive, but we still have a negative there, which is a negative. If I plugged in a 3, same thing. Positive, still be a negative, which is a negative. Anything big above 4 gives me a positive. All right, so you go positive, negative, negative, positive. So it's increasing from negative infinity to 0, union 4 to infinity. And it's decreasing. Now, so we gotta be careful and why the asymptote is important. Normally, we just do 0 to 4, but because of the asymptote, you have to split it up. So 0 to 2, union 2 to 4. Well, that's an awful 4, but you get the idea. All right, max and mins. The changes at 0. That is a max point. And min, it changes at 4. It goes from down to up, which is that. So we are going to the original here, which the original is, whoops, sorry about that, is way up. It's right there. So when I plug in 0, I get -2. So I get -2 when I plug in 0 because that is already the intercept. Know that. When I plug in 4, 4 would be 16 minus 8, which is 8. 8 plus 4 is 12. 4 minus 2 is 6. So I would get 6 when I plug in 4. So I get 4, 6. Remember, these go back into the original. All right, so then for the second derivative, the only critical value I get is 2 because the top 8 is never going to be equal to 0. So 2 makes the bottom equal to 0. So, but remember that is an asymptote. So I plug anything into the left, like 1. 1 minus 2 is a negative number. Negative number cubed is still a negative number. Anything bigger is a positive. So concave up from 2 to infinity. Concave down from negative infinity to 2. Points of inflection. It changes at 2, but that's an asymptote. So there are none. All right, there are none. All right, any questions on anything with the first and second derivative? Again, all stuff we've done before. So now we move on to our big number line. And we put all our critical values on there, which only were 0, 2, and 4. All right, 0, 2, and 4 were our critical values. It was increasing less than 0 and greater than 4. Between 0 and 2, it was decreasing, and 2 and 4, it was decreasing. It was concave up greater than 2, and it was concave down less than 2. All right, remember the curves, increasing it down, decreasing up, increasing up. Okay. So now to actually graphing it. So here we have asymptotes. We have a vertical asymptote at 2. So we have to graph that here the best that I can. We also had a slant asymptote that was y equals x. That is a line that goes through the origin that goes up at a with a slope of 1. All right. So you just got to be careful. This one, it's not going to be, you're going to be able to, you have to be as precise, but just at least where the lines intersect, because when you plot your other points, you want to make sure you're in the right little quadrant. Now, before we plot any points, if you remember graphs like this, like if we have our slant asymptotes like this, if you remember, graph the curve, if there's a curve here, that means there's normally a curve here. If there was a curve on the big part, that means it's opposite in the big part there. And that's the way it normally works out. And you'll be able to see that once we do our points, but it helps to have that knowledge of what the graph should look like anyway. So if we do our points, remember, there was no x-intercept. The y-intercept was at 0, I believe it was -2. Yeah, it was. All right, 0, -2. We had a max point at 0, -2. 4, 6. And then I'll just call this 6 up here. We had a point up here that was a min, and we had no points of inflection. So those are only 2 points, right? Those are only points. So less than 0, it's increasing down. So you can kind of tell it's going to be, it should look like this, right? This little curves, right? Because we have our points in those curves. So If I do increasing it down, it looks like this. Decreasing it down. It's like we have our own little, they're not quite parabolas, but you know what I'm talking about. And we got decreasing and up and increasing and concave up. And there's a graph. And you can see how those curves match up, increasing and down, decreasing and down, decreasing and up, increasing and up. And it follows the pattern that we've learned way back when, how slanted acid does. But even if you don't remember that, you still will be able to get what the graph should look like. And going back and talking about symmetry, you can see how this is not symmetric about the y-axis. If something was even, you'd be able to flip it over and be the same thing. If it was odd, it would be like perfectly, like if I rotated it 180 degrees to be the same picture, this would not be. So even if you can't figure out symmetry algebraically, you can check yourself when you do the actual graph. All right, questions? So what I'm going to ask for you guys to do over the weekend is this problem here, which is same type of problem where I give you the first and second derivative. You're going to go and solve. There's going to be asymptotes and so on. All right. So I will repost in the classroom. This is actually from the worksheet that you guys did the first night with all the limits and stuff. So I'll repost that. And what I'm going to say is do section 2. That's right here. Summary of curve sketching. Number 1, we just did A in class. You guys are going to do B. So it's this one right here, section 2, number 1B. So when I say that, hopefully you guys understand which problem I'm talking about. All right. So as soon as I log off here, I will put that assignment up there and then just have that done by next week. And then we'll move on from there. All right. Any questions? All right. I hope you guys enjoy your weekend, and I'll be talking to you guys on Monday.
Thank you. Have a good weekend.
Thanks. You too.